Imagine you have a billion records: phone contacts, financial transactions, server logs. How do you find one specific entry? If those records are unsorted, you have no choice but to check them one by one, and in the worst case, you'll look at every single record before finding what you need. That's a billion comparisons. But if those records are sorted, you can use binary search. Binary search cuts the problem in half at every step. 1 billion elements takes just 30 comparisons. 30. That's the difference between impossibly slow and instant. But to unlock binary search, you first need your data sorted. And the most reliable, scalable algorithm for doing that is merge sort. In this video, we'll build it from the ground up: the intuition, the code, the complexity, and the real-world places it shows up every day. Before we can appreciate merge sort, we need to understand what we're replacing. The most intuitive sorting approach is bubble sort. You scan through the array, compare adjacent elements, and swap them if they're in the wrong order. Repeat until nothing moves. It works, and it's easy to understand, but it's brutally slow. With 100 elements, you make around 10,000 comparisons. That sounds fine, but scale up to 10,000 elements, and you're looking at 100 million comparisons, about a second of work. Scale up to 1 million elements, and you're at 1 trillion comparisons. That's 12 days on a modern machine doing nothing else. This is what O of n squared means in practice. The number of operations grows as the square of the input size. Double the data, and you quadruple the work. The problem isn't the algorithm. The problem is the approach. Comparing adjacent elements and fixing one inversion at a time is simply not how you sort efficiently at scale. We need something fundamentally different. Here's the key insight behind merge sort. Merging two already sorted arrays is incredibly easy. You put a pointer at the front of each array. Compare the two front elements. Take the smaller one, advance its pointer. Repeat. You touch each element exactly once. That's O of n, linear time. Now here's the recursive leap. What if both halves of your array were already sorted? Then you just merge them, and you'd be done. But how do you get both halves sorted? The same way. Sort each half by splitting it in half and sorting those halves. This continues recursively until you reach arrays of one element, and a single element is trivially sorted. This is the divide and conquer pattern. Divide the problem into smaller subproblems. Solve each subproblem recursively, then combine the results. For merge sort, that means 3 phases. First, divide, split the array at the midpoint. Second, conquer, recursively sort each half. Third, combine, merge the two sorted halves back together. Simple in concept, powerful in practice. Let's trace through the split phase with a real array: 38, 27, 43, 3, 9, 82, 10. At level 0, we have all 7 elements. We find a midpoint and split into 2 halves. The left half is 38, 27, 43, and the right half is 3, 9, 82, 10. That's level 1. We keep splitting. The left half splits into 38, 27, and a singleton 43. The right half splits into 3, 9, and 82, 10. That's level 2. One more split. 38, 27 becomes 38 and 27. The pairs 3, 9, and 82, 10 each split into 2 singletons. Now at level 3, we have 7 individual elements: 38, 27, 43, 3, 9, 82, and 10. Each is a single element, and a single element array is always sorted by definition. This is our base case. The recursion stops here. Notice the shape of what we just built. It's a binary tree. Every split creates 2 children. The depth of that tree is log base 2 of n. For 7 elements, that's roughly 3 levels. That log in depth is the key to why merge sort is fast. The merge operation is the heart of the algorithm. So let's walk through it step by step. We have 2 sorted arrays. Left is 3, 27, 38, and right is 9, 43, 82. We place one pointer, I, at the start of left, and another pointer, j, at the start of right. We create an empty result array and start filling it. First comparison. Left at I is 3, right at j is 9. 3 is smaller, so we take 3 and advance I. Second comparison. Left at I is now 27. Right at J is still 9. 9 is smaller, so we take 9 and advance J. Third comparison. 27 versus 43. 27 wins. We take it and advance I. Fourth. 38 versus 43. 38 wins. Advance I. Now the left array is exhausted. We append all remaining right elements, 43 and 82, directly into the result. Final result, 3, 9, 27, 38, 43, 82. Fully sorted. And critically, we touched each element exactly once. The total work to merge two arrays of combined length n is O of n. That single linear scan per merge level is what gives merge sort its speed advantage over quadratic algorithms. Now let's watch the merge phase rebuild our original array from the bottom up. We start at level 3 with 7 singletons, 38, 27, 43, 3, 9, 82, and 10. Each is trivially sorted. Now we merge adjacent pairs. 38 and 27 merge into 27, 38. The singleton 43 stays as is. 3 and 9 merge into 3, 9. 82 and 10 merge into 10, 82. That's level 2 for sorted subarrays. One more level of merges. We merge 27, 38 with the singleton 43 to get 27, 38, 43. We merge 3, 9 with 10, 82 to get 3, 9, 10, 82. That's level 1. 2 sorted halves. Now the final merge. We combine 27, 38, 43 with 3, 9, 10, 82 using our two-pointer technique. The result is 3, 9, 10, 27, 38, 43, 82, the fully sorted array. Notice what happened at each level. We did merges that together touched all n elements exactly once. 3 levels of merging, each costing O of n total work. That's why the overall complexity is n times the number of levels, O of n log n. Let's look at the Python implementation. The merge sort function is clean and short. If the array has 1 or fewer elements, return it immediately. That's the base case. Otherwise, compute the midpoint. Recursively call merge sort on the left half and the right half. Then merge the 2 sorted results and return. That's it. 5 lines of logic. The merge function does the actual work. Initialize an empty result list and 2 pointers, I and j, both starting at 0. While both pointers are in bounds, compare the current elements. If the left element is less than or equal to the right element, append it and advance I. Otherwise, append the right element and advance j. When one side is exhausted, extend the result with whatever remains in the other. Return the result. Notice the less than or equal comparison. That's what makes merge sort stable. When elements are equal, we always take from the left first, preserving original order. If we use strict less than, equal elements could flip order, breaking stability. Run this on the array 38, 27, 43, 3. It recursively splits into pairs, sorts each, and merges back into the sorted result 3, 27, 38, 43. Why is merge sort O of n log n? There are 2 observations that explain it completely. Observation 1. The recursion tree has log base 2 of n levels. If you start with 8 elements and keep having, you reach singletons after 3 levels. Log base 2 of 8 equals 3. More generally, having n things repeatedly takes log n steps. Observation 2. At every level of the recursion tree, the total amount of merging work is exactly n. At the top level, you merge 2 halves of size, n over 2 each. That's n comparisons total. At the next level down, you merge 4 groups, but together they still add up to n elements, again n comparisons. At every level, regardless of how many submerges are happening, the total work across all of them is n. Multiply. N work per level, log n levels, gives O of n log n total. And here's what makes merge sort special among fast sorting algorithms. This bound holds for the best case, the average case, and the worst case. There's no bad input that degrades it to quadratic behavior. Unlike quicksort, which can hit O of n squared on already sorted or adversarial input, merge sort is completely predictable. Every time in log n. Merge sort's main cost is memory. During every merge, we can't merge two arrays in place. We need a temporary buffer to hold the result. When we merge the two halves of size n over 2 each, we allocate a temporary array of size n. That's O of n auxiliary space. The recursion call stack also uses memory, 1 frame per level of recursion, so O of log n for the stack. The dominant cost is the O of n for the temporary arrays. Compared to insertion sort and heap sort, which sort in place using O of 1 extra memory, merge sort is more expensive on the memory side. Quicksort uses O of log n average space for its call stack and also sorts in place. So why use merge sort at all? Because the trade-off is often worth it. Merge sort gives you a guaranteed O of n log n time. Quicksort can degrade to O of n squared. Merge sort is stable, quicksort is not. And for external sorting, the O of n space model maps perfectly to writing temporary files to disk. Choose your algorithm based on your constraints. If memory is tight, consider heap sort. If stability and worst-case guarantees matter, use merge sort. A sort is called stable if equal elements keep their original relative order after sorting. This sounds like a small detail, but it's important in practice. Imagine you have a list of students sorted alphabetically by name: Alice, Bob, Charlie, Diana. You want to sort them by grade. With a stable sort, all students with an A grade appear before B students, and within each grade group, the original alphabetical order is preserved. Alice and Bob stay in order among the B students. Charlie and Diana stay in order among the A students. With an unstable sort, the within-grade ordering is unpredictable. You might get Diana before Charlie, even though Charlie came first alphabetically. When you chain multiple sort operations, sort by date, then by name, you need each sort to be stable or the earlier ordering gets destroyed. Now, why is merge sort stable? Look at the comparison in the merge function. We use less than or equal. When the left element equals the right element, we take from the left first. This guarantees that elements from the original left half always stay ahead of equal elements from the right half. That single decision, less than or equal instead of less than, is what makes Python's sorted function and Java's collection sort stable. Merge sort is everywhere in production systems, often under different names. Python's built-in sort, list.sort, and the sorted function, uses an algorithm called Timsort, invented by Tim Peters in 2002. Timsort is a hybrid of merge sort and insertion sort. It identifies already sorted runs in the data and uses insertion sort for small ones, then uses merge sort to combine them. The result is an algorithm that's as fast as merge sort in the worst case, but dramatically faster on nearly sorted or partially ordered real-world data. Java's collections.sort uses the same Timsort algorithm since Java 7. Java's Arrays.sort for objects also uses Timsort. Merge sort also shines in the big data world through external merge sort. When you have a terabyte of data to sort and only 16 gigabytes of RAM, you load chunks, sort them in memory, write sorted runs to disk, then do a multi-way merge across all those runs, reading from multiple files simultaneously, always taking the smallest front element. The sorted output streams out without ever having the full dataset in memory. This is how databases handle order by clauses on large tables that don't fit in the buffer pool. And for linked lists specifically, merge sort is the preferred algorithm. No random access needed, just pointer manipulation. Quicksort on a linked list is painful. Merge sort is natural. Let's put it all together. Merge sort is a divide and conquer algorithm with 3 phases. Divide, split the array at the midpoint, recursively all the way down to single elements. Conquer, single elements are trivially sorted. That's the base case. Combine, merge sorted has using the 2-pointer technique. Time complexity, O of n log n, best case, average case, and worst case. No exceptions, no degenerate inputs. Space complexity. O of N auxiliary memory for the temporary merge buffers. Stability. Yes, merge sort is stable. Equal elements always preserve their original relative order. When should you choose merge sort? Use it when stability is required. Use it when you need guaranteed O of N log N without the risk of quicksort's worst case. Use it when sorting linked lists. Use it for external sorting when your data doesn't fit in memory. Avoid it when memory is tightly constrained and heap sort or in-place partitioning sorts are more appropriate. Merge sort is one of the most fundamental algorithms in computer science. It underpins Python's sorted function, Java's collection sorting, and distributed data processing at scale. Once you understand merge sort, you understand divide and conquer, and that pattern shows up everywhere. Thanks for watching. If this was helpful, subscribe. We cover one algorithm or system design concept at a time from the ground up.